Hey everyone, my name is Dr. Paul Kerstetter, and today I want to talk about decimation FIR filters. Decimation filters play a critical role in software-defined radio systems. In this video, I'll start with a high-level overview of an FM software-defined radio, then dive into the FIR filters, specifically why decimation filters are needed and how they fit into the signal chain. I'll also explore FIR filters using a filter design tool called T-Filter to highlight key design trade-offs, and then take Vivado for a spin to show you how to implement decimation filters using the FIR compiler GUI. Let's get started. Here is the presentation, FIR Decimation Filters Explained, an essential element of software-defined radios. In this slide, we see a typical FPGA application where decimation filters are used. A software-defined radio, specifically an FM radio receiver. From left to right, the FM signal passes through a 20 MHz bandpass filter and is then oversampled by an ADC operating at 160 MHz, 8 times oversampling. The ADC digitizes the analog waveform and delivers the samples to the FPGA. Inside the FPGA, mixers translate the signal to baseband and separate it into two quadrature channels, I in phase and Q quadrature, using local oscillators that are 90 degrees out of phase. Since individual FM channels occupy 200 kHz bandwidths, a low-pass filter is used to select a single channel, determined by the LO frequency, F0. Because the 160 megasamples per second sampling rate is far higher than required for audio processing, decimation filters are used to reduce the sample rate. Finally, the signal passes through an FM discriminator or demodulator to recover the audio. At this point, a natural question arises when viewing the SDR diagram. Why do we need both a low-pass filter and a decimation filter? The short answer is that using a single filter is impractical, and in many cases using more than two filters is actually beneficial. To understand why, let's turn our attention to FIR filters. Let's start with a quick refresher on the theory that brings us to FIR filters. When a signal passes through a linear time invariant system, the output is the convolution of the input with the system's impulse response. This is expressed using the convolution integral for continuous time systems, shown in the slide. Solving the convolution integral directly can be difficult, but in the frequency domain it becomes much easier. Using the Fourier transform, convolution becomes multiplication. Since FPGAs operate in the digital domain, we use the discrete time version of the convolution equation known as the convolution sum, which is shown in the slide. K is an integer that represents time steps. It is tied to the sampling interval Ts. This lets us bridge the gap between the continuous and discrete worlds. Let's take a simple case where n equals 2. The convolution sum equation becomes the equation shown in the slide. From the equation, we can see adders and multipliers are needed. We also need delay elements since the input xn minus 1 is a delayed version of xn. Delay elements are flip-flops. Finally, gain elements are needed for the constants or coefficients, represented by h0 and h1. The convolution sum equation can also be represented graphically, which is shown in the diagram. This is known as the direct form architecture for n equals 4. Now that we've discussed where FIR filters come from at a high level, let's start turning some knobs. If we need a low-pass filter like the one shown in the SDR diagram previously, the first step is to define the filter requirements. For an FM broadcast receiver, a single channel occupies 200 kHz, which corresponds to a plus or minus 100 kHz baseband signal after mixing. This leads to a low-pass filter with a passband from 0 to 100 kHz, followed by a transition band of approximately 220 to 30 kHz and a stop band beginning around 120 kHz. According to the SDR diagram, the sampling rate is 160 MHz, which is far higher than required for audio processing and strongly motivates the use of decimation filters. In addition, the filter design requires specifying the allowable passband ripple and stopband attenuation. Typical values are on the order of 0.05 dB ripple in the passband and 60 to 80 dB attenuation in the stopband. These parameters are illustrated in the slide where I use T-Filter, a free online FIR filter design tool. Notice that the sampling frequency in the diagram is set to 400 kHz. In the next slide, I'll explain why I didn't use 160 MHz for this example. Roughly speaking, the number of coefficients or taps required by an FIR filter follows the relationship shown on this slide. The constant A depends on the required stop band attenuation and the type of filter design being used, such as windowing methods or Parks-McClellan algorithm. In our case, the filter is designed using the Parks-McClellan method available in T-Filter. Fs is the sampling frequency and delta F is the transition bandwidth, the range of frequencies over which the filter rolls off from the passband to stopband. As you can see, the number of coefficients is proportional to the sampling frequency and inversely proportional to the transition bandwidth. From the previous slide, we set the transition bandwidth to 20 kHz and the sampling frequency to 400 kHz. Now, if we increase the sampling frequency to 160 MHz, what do you think would happen? The answer to the question is on the slide. 40,000 coefficients. What really drives FIR filter complexity isn't the absolute bandwidth, it's the transition bandwidth relative to the sampling rate. 40,000 coefficients, or taps, represents an enormous burden on FPGA resources. Using the FIR compiler IP, this would translate to roughly 1 DSP slice per coefficient, or about 40,000 DSP slices. For context, a Zynq UltraScale Plus device has on the order of 2,000 DSP slices, so this approach is simply not feasible. While it's true that a hand-coded FIR filter doesn't strictly require DSP slices, it still needs 40,000 multipliers, which is equally impractical. So how do we solve this problem? Let's move on to the next slide. The solution is to use a multi-stage decimation filter architecture. But before showing you that, you might be wondering, what is decimation? Decimation is simply reducing the sample rate by discarding data in a controlled way. For example, consider a data pipeline with a 10 MHz input clock and a 5 MHz output clock. If we did nothing, data would accumulate because samples are arriving twice as fast as they are leaving. To keep the system running in a steady state, every other data sample must be discarded, which is what is shown in the slide. That process combined with filtering to prevent aliasing is what we call decimation. You may be wondering how we can throw data away and still expect a useful result. The answer lies in Nyquist's sampling theorem. Simply put, to preserve all the information in a band-limited signal, we must sample at a rate of at least twice its bandwidth. In the example from the previous slide, the output sample rate is 5 MHz, which means the Nyquist frequency is 2.5 MHz. Therefore, the low-pass filter must roll off below 2.5 MHz to satisfy the Nyquist criterion and prevent aliasing. In the case of an FM software-defined radio, we start with a 160 MHz sample rate, but we are only interested in a single FM broadcast channel. An FM broadcast channel occupies about 200 kHz of bandwidth. To preserve all the information in that channel, Nyquist tells us we need a sampling rate of at least 400 kilosamples per second. This is why decimation filtering is so powerful. It lets us safely reduce the sample rate from 160 MHz down to a few hundred kilohertz while retaining all the information we care about. Now that we have the basics, let's design our filter chain. To cut to the chase, the complete design is shown in the diagram. The chain consists of 4 FIR milk filters, 3 of which perform decimation. For each filter, the diagram shows the decimation rate along with the corresponding input and output sampling frequencies. The decimation rate is defined as the input sampling frequency divided by the output sampling frequency. The specifications for FIR filter 4 from the previous slide are shown here. As you can see, since we are using 4 filters for the design, we are off to a good start with a 200 coefficient filter. By cascading multiple filters, we relax both the transition band and the sampling rate requirements. At this stage, the sampling rate is 800 kHz and the transition band is 20 kHz. Let's design the filter that precedes the final stage FIR. In other words, FIR decimation filter 3. We'll assume a decimation rate of 10, which means the input sample rate is 800 kHz times 10 equal 8 MHz. The output sample rate is therefore 800 kHz. By the Nyquist criterion, the post-decimation Nyquist frequency is 400 kHz, so the filter stop band must begin at 400 kHz or lower. If we choose a passband edge of 200 kHz, this gives us a transition bandwidth of 200 kHz. With this relatively wide transition band, the required filter complexity is modest, and the number of coefficients is on the order of about 20. Roughly 20 taps depending on ripple and attenuation requirements. Since the basic idea from the previous slide is repeated for FIR decimation filters 2 and 1, I'll fast forward and focus on the number of coefficients required for each filter. For FIR filters 1 and 2, the number of coefficients is shown in the slide. 20 for filter 2 and 20 for filter 1. If we sum the coefficients across all stages, we end up with approximately 260 coefficients total. Compared to a single stage design requiring 40,000 coefficients, this represents a dramatic reduction in complexity, saving well over 93% of the required multipliers and coefficient storage. Okay, that's the end of the presentation. In the next part of the video, I'll demonstrate how to use T-filter and show how the number of coefficients increases or decreases based on the sampling frequency and transition bandwidth. I'll also walk through Bravato's FIR filter IP core and highlight how to implement decimation filters. This is the T-filter part of the demonstration. To get T-filter, just type T-filter in Google and you should be able to find it. It seems like a very nice, handy FIR filter design tool. In this case, what I have shown here is the filter for FIR decimation filter 3, which a quick reminder of what the specs are for that is shown here. But those specs are entered in this table below. We have a passband from 0 Hz to 200 kHz. We have a stop band from 400 kHz to 800 kHz. The delta frequency for the transition band is 200 kHz. And I have the sampling rate set at 1600 kHz. So that makes the frequency 800 kHz in the stop band, the last frequency. So you hit design filter and it gives you this nice filter with equi ripple in the passband and the stop band because it's Parks-McClellan. So these are the coefficients over here. You can get it both in the double floating point form or you can get it in the integer form. In the integer form, it's easier to see that the coefficients are symmetric. It starts off with 32 and 43 and it ends with 43 and 32. So they're symmetric about the middle. And down here it says we have 27 taps or coefficients. So what happens if I double the sampling frequency? Let's put that at 3200 kilohertz. And let's put the stop band, let's extend the stop band frequency, the last frequency, to 1600 kilohertz. And we'll do design filter. And the number of taps went up to 57. So we went from 27 to 57 coefficients here and here are all the coefficients. So it's close to a doubling of coefficients when we double the sampling frequency. So that means that the number of coefficients or taps is proportional to the sampling frequency. So next thing I'm going to do is I'm going to double the transition bandwidth. So right now it's 200 kilohertz because it's 400 kilohertz minus 200 kilohertz is 200 kilohertz. I'm going to double that. So I'm going to put the pass band or the stop band start frequency to 600 kilohertz. So 600 kilohertz minus 200 kilohertz is 400 kilohertz. So that doubles the transition frequency band. And then I'm going to design the filter. And now we're back to 27 coefficients. And here's our 27 coefficients. So the next step was, if we go back to the filter we started off with in this demonstration, I copied these coefficients here. Actually, I copied the double floating point numbers, and I copied them into Vivado. So let's go to Vivado. And this is the project that I talked about in a previous video about how a mixer works in an FPGA. And so that's the code for this. And so this is the first filter after the mixer right here. And to get that, you go to IP catalog and you type in FIR filter, and there's the FIR compiler. So you double click on that, fill it out, and then it puts it in your project. As a side note, a lot of times in SDRs, the decimation filter, the first stage decimation filter is a CIC filter. And it just so happens Vivado offers a CIC compiler, which you can use. But for this purpose, for this demonstration, we're using the FIR filter compiler for our decimators. The CIC compiler topic is a topic for another video. But we're using the FIR compiler in this case, and I'll show you what I did. Let's double click on that. And I've already saved all the changes that I made. So let me just go through the changes I made. The first thing I did is I took my T-filter coefficients and copied them in here in our coefficient vector. And as you can see, it has 27 coefficients, which is what we started off with in T-filter. And the next thing I did is I changed this to decimation. It was set at single rate in the old project, but in the new project I set it to decimation. I set my decimation rate value to 10 since that's the amount of that's the decimation rate for our filter that we're using for our FIR filter number 3. The channel specification has an input sampling frequency of 8 megahertz, a clock frequency of 8 megahertz, and it says here, it kind of summarizes what's going on. It says there's one clock cycle per input and 10 clock cycles per output. So that shows that we're decimating by 10. And our implementation, we have an input data width of 10 and an output data width of 27. That's probably going to up the actual vector in the code to 32 though. So because it has to be on 4-bit boundaries. Here's the way you can change it. If your coefficients are symmetric, it'll probably automatically come up to inferred. And if you don't want it to take advantage of symmetric filter coefficients for using up less resources, then you can click on non-symmetric. And detailed implementation actually shows you how many DSPs we're using. Since it's a decimation filter, it's actually only using 3 DSPs instead of 1 DSP per coefficient. It's using 3. If we go back and change our decimation rate to just 1, and then then it matches the number of coefficients as 27. And so now we're back to 3. So that's how you set it up. And you can look in these windows over here, and that shows you it has an input clock. And so basically internally it divides that clock down by 10 so that it can decimate. So you don't have to be responsible for an output clock. You just put an input clock. You just have to remember that you're decimating by a factor of 10. And this is also a neat little window here, frequencies response. And this looks a lot like our T-filter response. So that's a good thing to check to make sure that the GUI understands what kind of filter you have, and that looks like what it should be. That's all now for the Vivado demonstration. I hope you enjoyed this video. If you enjoyed this video, please like it and subscribe to the channel. Stay safe, and I'll see you in the next video.